Hey class. So I wanted to start today's lecture by discussing um, the uh, the zeta function. It eventually became known as the Riemann Zeta function. Although Euler, right, who I've mentioned once or twice in this course before, spent some time studying it as well. So we'll begin with his approach, and then we'll make some comments on uh, results of Riemann, and then we'll do the the college equivalent of popping in a video and watching that for the rest of the class. We'll work through an Angular JS tutorial, and we'll spend a couple of minutes setting up an ExpressJS backend. So I wanted to present you with alternatives to the C# API that I demonstrated briefly last time. And this time I wanted to spend, instead of so much time on the back end, show how you can quickly set up something there that'll at least serve up data. And then, so it's the complementary side. So last time we set up the back end, and then we used Postman to test the results, as an artificial client. And while Express can be configured to be more than an artificial backend, it is a really handy utility as far as frameworks go, in order to quickly set something up that actually is, servicing network traffic to localhost. You can configure it to work over the network if you want. And helping to support the development of a front end. So we'll play around with that. We'll go as far as we get, and then you're certainly welcome to continue the tutorial on your own. Okay, so the zeta function is a generalization of two of the series that we've looked at so far. So we've discussed the harmonic series. Okay, so the harmonic series is this one, right, where the denominator uh, has it iterates over the entire collection of natural numbers, and it's raised to the first power, or not raised to a power if you prefer. And the series diverges, as we've demonstrated, using the argument that uh, so that we can continue to group these numbers that are greater than whatever constant we choose. So in this case, we're demonstrating that the sum is going to be greater than whatever this first, or the ensuing term is, right? So here, this is greater than 1/2. This pair is going to be greater than whatever this next term is, so a quarter. Or term-wise, they're all greater than whatever the one following the collection is. So two, or these two are going to be greater than a fourth, and the next four will be greater, term by term, greater than an eighth, which will add up to, again, something greater than half. And so even though the terms all go to 0, it adds up to infinity. It diverges off to infinity as you add terms to the sequence. Okay, so and then we've also discussed the geometric series, where we raise it to the second power. Okay, so not quite exactly the same thing. But it is an example of a geometric series, which we'll touch on in a second. And I guess the series that I had intended to show you before my uh, uh, switching tracks prematurely was the result that we studied. I forget how many lectures ago, but where we raised this to the second power and we got the result of pi squared over 6. So. Okay, so we can imagine a series where we just play with the power of the terms in the denominator, and in fact, that is what the zeta function has done. And so it's represented by that. So we'll just leave that as a footnote for now, and we'll come back and discuss it later. But first, we're going to bridge the notion of a geometric series with this harmonic series, and then we'll generalize that to something of this form. And then once we've done that, we'll discuss some of the other ways that the problem was analyzed. Okay, so a geometric series is something of the form where you have some initial or some initial value where a is a constant. So for now, we'll just leave it at 1, but we'll show that it could really be anything. And then you have some ratio, which is less than 1. Right? So so we can choose it to be 1 over 2, 1 over 3, 2 over 3, 1 over 4, etc. Right? Just anything where the denominator is larger than the numerator. Then we can consider the series. So starting with the a equals 1, and then we'll generalize it. 1 plus 1 times our ratio r. So for now, we'll start with 1/2, then we'll do it again with with 2/3, and then we'll play around with it a little. Okay, so um, let me just change the notation. Okay, so all of the other terms are there, and we go up. We have n terms where we go from the power 0 all the way up to the power n minus 1. So there's n terms here. We don't know what that equals. It's going to be something, right? So we'll just note it as the sum is equal to something. Okay. So we'll call it S. Okay, so we can play with it. We can get a new series by multiplying our ratio 1/2 times this series. So okay, well, this new series that we generated looks an awful lot like this previous one. So there's got to be a way that we can manipulate that, right? So yeah, let's just start getting rid of terms. Let's see if we can solve for S by just deleting as much as possible. So we could go in either direction, but the easiest way to do is to start with what appears to be the larger one, because this one's vanishing, and remove each of these terms. Right? So so then our first series minus our second series is 1, and then this term is canceled out by this term. This term is canceled out by this term. This term is going to cancel out whatever was going to be the next one over here, and so on. And then the n minus 1 term over here is going to cancel out this one. So that we're left with something in this form. Okay, well, we wanted to solve for S, so let's just pull it out over here. So it's this is equal to S times 1 minus 1/2, which is just our it happens to be our ratio, but if we want to solve for S, then we just need to move this over to the right hand side. So we'll remember that this is 1 minus 1/2. Okay, so now we'll just move it over. And remove it from the left-hand side, right? So we divided both sides by this by. Okay, so S is equal to this divided by this. Okay, so that's nice as a one-off. Can we learn something from it? Is there some pattern that we can extract? Sure. We did it this time with 1/2, but we've already studied that geometric series before. Let's play with the ratio a little. So this time let's choose 2/3. Okay, so again we have n terms ranging from 0, or the ratio to the power 0, all the way up to the ratio to the power n minus 1. And again, we know it adds up to something, right? So we'll set it equal to s. So again, it looks like we can generate or cancel out most of the terms in this series because it follows this really simple pattern that if we just multiply each one of them by this ratio, then do our subtraction trick, we could cancel out all but 2, the first and the last term. So okay, so again we have n terms, this time to the power 1 all the way up to the power n. Do our subtraction trick. Okay, so the first term, and then everything else seems to cancel, so and then we're just left with this first term minus this last term. Okay, because we're subtracting this series, so everything up here is positive, everything down here is negative because of the subtraction. And then pull out s again. So then our sum is equal to 1 minus that last term divided by 1 minus 2/3. Okay, so I left this 1 out here as multiplication. So the series is a progression where we multiply whatever that start value is by some ratio every time. Does it matter that that start ratio is 1? Can we choose something else? No, it it doesn't matter. Okay, so let's take a look at that. Okay, so we defined A, and previously we'd said let it be 1. Now let's just let it be in R. And now, instead of picking, 1/2 or 2/3, we'll just say that we have some ratio, and we're fixing it between 0 and 1. Although the results would hold in general, except for the limiting case that we'll talk about. So, but for now, just assume that it's between 0 and 1. Okay, so we have the same series, or something that's of the similar form, in terms. Each of these are multiplied by a, whatever our start value is, and then raised to the power of 0 all the way up. Okay. And they all share that a, so we could just strip that out. So let's do that. Okay, so it's nice to note, but so we can do that, and we can think of it in those terms. But let's leave the a in for now because we're going to use it to do our cancellation trick. So we'll put it back in. And we'll move the series forward one term. Right? So multiply every term by r, and we get okay, so again, in terms, and they agree on all except the first in this first series and the last in the second series. Uh, so we'll do our cancellation trick. So this first term survives, and then this is canceled by this. Pull out S again. Then we move it to the right side. Okay. And so we end up with this formula. So it turns out that the numbers were just getting in the way. We never actually needed them. We could plug them in at the end. And series of this form have a summation that can be computed pretty quickly. So if n is finite, then r can be anything other than 1. Right? So if it's 1, you don't need this trick, right? So if r is 1, then you have a times 1 plus a times 1 plus a times 1 n times. Okay, well that's just a times n. You don't need some mystical geometric series to compute that value. So this is for all of the other cases when you're not adding a plus a plus a plus a, n times. Okay, so in those cases, what is the value? Okay, so let's simplify this just a little bit. And we get this ratio. So a comes out of the numerator. R to the 0 was 1, so we just simplify that to 1. And we get 1 minus r to the n divided by 1 minus r. Okay, so that's a pretty nifty result. So again, that works whenever r is not equal to 1. And in the okay. So in the case that n goes off to infinity, that we have an infinite series, then now we actually need to enforce this. So this works for any value n and any value r other than r equals 1. So in that case, you can actually just plug in the numbers and you get something. But if you have an infinite summation, then you're going to run into trouble if you try to apply this. If r is greater than 1, or greater than or equal to 1, because this term won't go away. But if it's less than 1 and n goes to infinity, then something that's between 0 and 1 raised to infinity is just going to vanish. So as n goes to infinity, Don't know if you can see that, but that's actually a 0, right? R to the n is 0. So then you get something of this form, where it simplifies to just a divided by 1 minus r. Right? And again, that's if the ratio, if the absolute value of the ratio is between 0 and 1. So something that can disappear as you continue to take those additional terms. Okay, so that's the concept behind geometric series and the logic for deriving that formula. So let's try to let's do a little bit of work and try to relate that back to that series that we saw before. So let's just restate that. Okay, so the series was okay, so it's just the sum of 1 over n to the s. So Euler, who was a mad genius, right? He wanted to find the prime function. So if you look at his work, he defined this totient function, Latin for how many. And so it's the prime counting function. It's a theoretical thing. He assumed that, okay, well, if I could have such a thing, let me name it first, and by naming it, maybe I can bring it into creation. And so he did. It's phi of n or whatever for the number of primes less than some integer n. And you can imagine him casting about trying to find something. And so here's a problem where we have the entire set of integers considered, and he had this clever idea of trying to break it down, right? So let's define something similar to this in terms of the prime numbers, right? So yeah, so okay, so these series would have this form, right? So you consider the prime numbers in sequence, so 2, 3, 5, 7, 11, 13, 17, 19, and so on, right? And so then you give them something very similar to this form, but instead of iterating, he wanted to consider these, and these are the geometric series that we were just discussing, where we're considering this sequence of ratios, right? But the ratio is always 1 over that next prime number. And so this I'll note, and then we'll come back to it. I'll remove it because it just complicates the matter. But if we wanted it to look just a little more like this form, then we would raise it also to the power s. And it would just show up term by term, so that s would carry out term by term. But we'll leave it for now. Okay, so we were just looking at this, right? So we know that this has something of the form right? Like that was just the result that we had arrived at. And these are infinite series, so this vanishes, right? And then there is no a sitting out front. It's just 1. So a was the value that each of these ratios was multiplied by. So a is equal to 1. So that simplifies a little bit. Okay, and so how do we make this work for us? How do we manipulate this even further? So if we allow that ratio to vary a little bit, so now we're going to include the s, and I'll show that it carries through. Okay, so same trick, but I dropped the index, so it's just a generic prime number, and it's raised instead of to the n times s, so the s will carry through. Okay, so now we have that it's again a times 1 to the first term, right, minus the last term. Okay, and so the last term in an infinite series is going to vanish. And our ratio is this, right, where we've dropped the in. So R is equal to 1 over p to the s. So each term was the previous term multiplied by 1 over p to the s. Right? So 0, p to the 0s, p to the 1s, p to the 2s, and so forth. Right? So this is our ratio. So now we'll simplify it. So a was 1, so we just dropped that. N went to infinity, so this term went away. And R is equal to 1 over p to the s. So that's 1 minus 1 over p to the s, or we could rewrite it as 1 over 1 minus p to the negative s. Okay, and so that works for any prime. So how do we get back to this thing? Well, this is again where Euler was pretty clever. So he realized at some point along the way that he could leverage the prime factorization theorem. And that says that every integer has a unique prime factorization, so that it is the product of a distinct combination of primes and their powers. And so he you imagine he thought about it for longer than a minute, but maybe. I mean, you don't know how quickly his brain was firing at this point. And so he realized that he just needed something that would combine all of these fractions into some infinite series, right? So he again imagined some prime iterating function or something of that form, and he came up with what I think is a really clever representation of it. So we have that it's that this is equivalent to this. Now what we need is something that will permute these, like and give us every combination of primes and their powers in the denominator, because that's exactly what this is, right? So this is any prime raised to the 0. Okay, that's fine. And then this is 1 over 2 to the s, but so the s is kind of arbitrary. It's just sitting there, but it's 1 over 2 to the 1. This is 1 over 3 to the 1. This is 1 over 2 to the 2. 5 is 1 over 5 to the 1. 6 is 1 over 2 to the 1 times 1 over 3 to the 1. And so he just imagined this product series that would iterate over all of the primes. Okay, so we just showed the generic equivalence of this is equal to this, as far as the product is concerned, term by term. This is some generic prime, and this geometric series comes out to this because it's an infinite series, and that R into the NS vanishes. And so this was this, right? So there's that substitution. But then if you think about it, this is that series with the first primes, and it's all of those powers of 2, from 0 all the way up to any arbitrary power of 2, multiplied by a summation of all of the powers of 3 and so forth, right? And so every one of these series is going to have 1 sitting at the front, and then the powers, like if we go back to where we're selecting, so we're selecting one term from this series, so it's either 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 to the 3, and so forth. And so in that fascinating result, right? So whatever n is, it's going to have a prime factorization of this form, right? So n is an integer, and so it has this factorization, and it's 2 raised to some power, possibly 0, times 3 raised to some power, possibly 0, times 5 raised to some power, possibly 0. And so this is essentially the selection function for this, right? And it creates all of those combinations of all of the products of primes with each other. And that series, right, because of the distributive nature of this, right? So you end up with only the distinct combinations of all of those primes multiplied by each other, where they're all in the denominator, and then because this is summation, right, and you can see that you choose one of these so you make your multiplication each time you select from the summations, and you only get one value from that first summation, right, and one value from the second summation, and you get all of the combinations of distinct values from this one times distinct values from this one. And you never get any crossover where you have A times B or anything. Like, that's just the way the multiplication works. And it works even as you add more and more terms to this sum, right? And so, in this really clever way, he was able to show that this is actually just another form of this. And so he felt he was really onto something, and they were able to show some other results from this. But he was able to relate this sum of 1 over n to the s, so all of the natural numbers raised to whatever arbitrary power you have, was equal to this product of primes. And so this concept of prime numbers, which have since the beginning of philosophy evaded any function to pin them down, any prime generating function, he was able to come up with something that actually relied on just those prime numbers. And so it was, I think it's a fascinating result. And so these two are in fact the same, because this product generates this. It generates all of these combinations, right, of the natural numbers, each of which has prime factorization. And you're iterating over all of the primes, and you're selecting powers or whatever, and you end up with all of the combinations of them, and it simplifies into this beautiful formula. And so, whenever he studied it, that was the result that he came up with. But he, I don't believe he was able to do a whole lot more with it. But that then alone was a very clever representation of it. So the formula for it, there's a couple of different variations. But we already showed that, well, if S is 1, that this is going to diverge. And while Euler did a fair amount of work as far as developing theorems on the theory of complex numbers, the results for actually generalizing this to the complex plane, except for that point where we get the harmonic series when S is 1, was credited to Riemann. So we have it in these forms, but this is only whenever the real part of S is greater than 1. So whenever we haven't hit that infinity generated by the harmonic series. But there's this concept of analytic continuation, and we used it a little bit with the functional equation for the gamma function, and I mentioned that it had a pole, it shot off to infinity for all of the non-positive integers, and I kind of glossed over the fact that it's really only infinity at those points. But what about the complex numbers? So it's defined for the complex plane, except for those numbers where there's poles. So what about the part where it has a negative integer value, but a non-zero complex component? So I times something that's not zero as the input to that function. Well, it's not actually infinity, if you believe that. And so they were able to define this in the ambient range, where you get it for free. It's fully defined, and then they use the functional equation to go back one number each time to relate it to n minus 1 times gamma of n minus 1, right? That functional relationship. So the key was kind of extending it around that pole, like just creating this range and extending it there. And then complex analysis gives you some theorems. I'll say for free in that someone else had to prove them, but the analysis of functions which satisfy certain conditions in the complex plane, they are in some sense more well behaved than real valued functions, because whenever they meet this analytic requirement, they really meet it. They give you infinite differentiability. They give you certain uniqueness properties, where if it overlaps on some region, then it is the only function that does so. And so if you can come up with some continuation of this, then it is the unique representation of it. And so that it's really nice whenever you're discussing it to know that that you're looking at the function that you need to be working with. And so we'll discuss, or I'll note a couple of alternative forms of it for everything except whenever S is equal to 1, so except whenever this is the harmonic series. And you'll see that it starts to look significantly different pretty quickly. Okay, so in the same region that these two are defined, whenever the real part is greater than 1, we should now define S in complex terms, actually. Okay, so S is sigma, which is our real part, plus I times T, which is our complex component. Then we'll define this as an integral Okay, and again, you'll note that the parameter that we pass into this function is not actually the parameter that we define, or that we integrate with respect to. And so this is for sigma greater than 1. And this is actually the same thing as these two forms. And so you'll notice that this, whenever s is an integer, is s minus 1 factorial. Right? So there's this relationship between this and this up here, and so you can imagine that there's some integration by parts action going on. But what the observation that I enjoyed is, if you remember the way that we defined gamma of s, it's extremely close to this integral right here. So that it's actually, so that zeta of s is this ratio where they're essentially the same thing, except this one has e to the x minus 1 in its denominator, and this has an e to the x in its denominator. But aside from that, they're very similar integrals, and so the zeta is that ratio, which I think is a cool little tidbit or trivia or whatever. Okay, so we're still dealing with something that's to the right of the mountain, to the right of the harmonic series, that point where s equals 1, or a real part of s equals 1. So is there some more general definition? And yes, yes, there is. Okay, so that the functional equation, so for gamma we had the functional equation gamma of s equals s minus 1 times gamma of s. And for zeta, it's okay, so zeta of s for s not equal to 1. But now we can have real part of 1 just as long as the imaginary part isn't 0. Right? So zeta of s is equal to, on the whole plane, except for this point, 2 to the s times pi to the s minus 1 times psi, or sine of pi times s over 2, or pi over 2 times s, whatever, times gamma of 1 minus s times zeta of 1 minus s. So the functional equation is, in essence, the definition of a function where if you did it in English, it would drive your teacher insane. It's defining a function, something like recursively, but even worse than recursively, it's just defining the function in terms of itself, which it's not. It can be convenient in that it allows you to define it for the whole plane, right? So now we've had this trouble where we couldn't push it to the left of sigma equals 1, or less than or equals 1. But now we have this form where this 1 minus s tells us that if we can get s less than 0, then this 1 minus s, or real part less than 0, is going to be 1 minus a negative number, which would make it greater than real part of 1 for the input to this one, this reflected version. So really, we just need to define it in this range between 0 and 1, and this functional equation would in fact give it demonstrate that we can define it for the entire plane. And it's really interesting that gamma and zeta are so closely related. Like they show up in each other's, or gamma keeps showing up in its definition. And so there's this version which does define it conditionally, so non-absolutely, which I don't think it should really count, but there's this version of it that does define it in that range. And so you have to normalize it a bit by using an alternating series, and then that allows it to converge. So this is for the whole plane, but in that strip, the critical strip that we haven't defined yet, and so that defines it in that strip. And so yeah, there's quite a bit you could do by playing around with this function. Okay, so let's one more form for it. We'll just mention quickly. And so there's a contour integral. So this was for sigma greater than 1. But you can get that more general form for s on the plane, except for whenever it's equal to 1. If you leverage sine in gamma. Okay, so over here we're summing over the positive real line, but using that, I guess it was the Dirichlet series, I can't remember. You have this alternating term, and you still have this s to the minus 1, but now it's alternating. You have the same denominator. Gamma of s has moved over here, but now you have this sine of s, which is normalizing it. You have this imaginary component. And you have a contour integral. So the contour that he used was essentially over this real line. So this is the complex line, the imaginary axis, and this is the real axis, and so it goes around the real axis. But we'll mention it in passing later on. But whenever x is 0, you get so obviously s is dependent. It generates the series of integrals that we would discuss, and x is the variable of integration. And over here, we're integrating, with e to the x is the very first thing. So you get, some variation of 0 over e to the 0, which is 1 minus 1. So you get 0 in the denominator, which is part of why the real part had to be greater than 1, so that this is, somewhat mitigating this desire to shoot off to infinity at this first sampling of that integral. Anyway, so you're able to get it for the whole plane except for s equals 1 using this variation. But there's a theory that if you're integrating around a pole, then the contour in some sense doesn't really matter. All choices are equivalent because it's really the pole that for certain types of functions, for functions that meet certain conditions that are complex analytic. And so the pole is right there at the origin. So all that really matters is that the contour circles it, and it meets that condition. Okay, so let's switch over now, and we will do our tutorial and so forth for just a few minutes, and then I'll let you go. Okay. So we need to generate our application. So we'll call it just generic UI, because that's really all that we're aspired for in this one. Okay. So usually you'll do something like npm install either ng or Angular or AngularJS or JS or whatever. I forget what the actual install is. I think it's npm install ng. And I've already installed it, and last time we used like npx create react app and then foo UI. And so now we're not using the npm application. We're using that directly, ng and then new generic UI, and this is going to throw an error or not. It doesn't know what the application is. And so that would work on Linux and Windows if you're using this there, but it does not actually work for this, so we have to hack it a bit. So we're going to create a batch file or something that'll simulate the command that I want, and we're going to reference the location in app data roaming for npm packages that are installed globally, and we're going to get that Angular command ng.cmd, and then this forwards any arguments that we have. So the argument list that we pass in here will now be forwarded to this command, and it will execute that. Okay, so now now we can try running it with our bat command, and it's going to ask us some questions. Would we like routing? Yes, so routing is going to give us that the ability to change our locations, like change essentially directories or something similar, but for the web. We're going to use CSS, Sass, and SCSS, and all of these are essentially ways to break up the cascading style sheets that you're going to use. We're not doing enough to actually break that up, But it is a good habit if you're working on a large team and you're delegating areas. So you'll typically have one person that's doing all of the major styling, and then you'll break it up into these smaller components for CSS, and they'll do that styling locally. Okay, so it's creating our generic UI over here, and I said we'd create a backend for it. So that's our UI. Let's do a generic server over here. And the server is pretty simple. But we have to initialize the npm project ourselves, the node project ourselves. So the first thing you would want to do, if it'll let me, is having its reservations. Okay. We don't want to make it think too hard. Okay, well, we would want to install Express, and the way we would do that would be npm install Express /save, and that'll save it for our project. But we can't even get that far until we initialize our project. So it's doing a lot of that work automatically for us over here in the Angular project. But we need to kind of do it on our own. But we'll get there. For now, let's just create the placeholder documents. So API.js, this will create an Express server for us. I'll show you what that looks like. And if necessary, I'll create the package.json myself. But we require a particular JavaScript package, and that's going to be stored in node modules, which is the way that npm collects all of the dependencies that you're going to need. And so it's npm is really nice. Some people use Bower. I think there's some people use Yarn to manage it. But it always ends up in node modules because we're developing against JavaScript engine in Node.js. And so everything gets put in node modules and then managed in these package JSON files, or package lock or yarn lock or whatever you're using. Okay, so wherever it gets stored, we're requiring this from it, and then we're going to rely on some build scripts essentially to tell us how to execute the server. And it all makes sense in about 5 minutes, assuming that I have terminal access at that point. I do. Okay, so we'll get a chance to do it. Okay, so we want to create an app. We import our package, and it turns out that they've defined it as a function. So we just invoke that function, and it creates an application for us. We define the port that we want to listen on. Let's listen on 1, 2, 3, 4. Typically, other people will choose 3000, 3001, 8000, 8080, or whatever. It almost doesn't matter. You want to choose something larger than 1024. Port 80 is the actual inbound traffic for HTTP. 443 is for I think that's HTTPS traffic. 22 is SSH traffic. 21 is Telnet traffic. So things under 1024 typically have a meaning. Some database servers will leverage ports that are larger than 1000 or whatever. So if you get a collision, just try a different number. You have, in theory, 65,000 choices. Pardon me. Okay, so now we get to say where we're listening for that traffic. And anytime we get a hit here, so this is at the root level, so if they don't actually look for anything deeper, then our callback function, which we're defining right now, will be invoked, and it'll be passed a request object and a response object, which we will act against. But the request is all the inbound information, and this is what we want to respond with, or how we would like to respond to that. So we're doing just the most basic stuff. And so if we get a request there, just to make sure that we've configured our server correctly, then we'll invoke, or we'll reply with hello world. Okay, that's it. We've basically defined a web server. So now we just need to listen for the port. We can still write to the console because it's going to run as essentially a console application down here, and it'll listen. So let's just make a note to self. Web server started on port. We'll give the address. Okay, so let's try to run that and see how that does not work for us. Oh, okay, we have to switch directories. So cd into our generic server. Can't find Express. Okay, well, the reason that it didn't find it is because we didn't initialize our project. So it's pretty simple. We just yes, exactly as I suspected. We just run npm init. And you'll see that it's about to add a file over here called package.json. And then once we add express to that, then it'll add packagelock.json. Okay, so what do we want to name it? We want to call it generic server. Yeah, you can choose a different name, and typically whatever you choose here, if you're working with GitHub for source control, this will end up being the project name on GitHub as well. So you'll want to coordinate those. So yeah, for now, all of the defaults are fine because this is a throwaway application, but you may want to put some thought into them as you go by. Entry point is api.js. You can put the Git repository here, like I said, and coordinate that work. Yeah, all that's fine. Don't worry about it. So now we're going to go in and modify our package.json. So we have this script to run tests, and we don't have our test specified. And that's because this is really a throwaway app. So we can add an additional start script here for whenever we want to start our server. And this is strict JavaScript object notation, so JSON, right? JavaScript object notation. And so unlike in regular JavaScript where you can use single quotes or the backticks like I've been using everywhere, you have to use the double quotes whenever you specify a string here. And then you don't get to have the trailing comma here like I do everywhere. And so, but you can add this additional script, and it's node api.js, so calling our entry point. And so if we run npm start, it'll execute what's here. If we run npm test, it'll execute what's here. But that's all well and good. Now we need to add ExpressJS. So let's take a second to do that. So npm install express, let's just save. Okay, and npm start. Listening on 1, 2, 3, 4. Let's verify that claim. Hello world. Okay, well, I mean, that could really be anything. Is there any way we can test that again? Sure. So let's stop our server. And we'll change this to the worm has turned. Okay. It's a little weird. So we should be able to tell that it's not just some relic. Okay. All right, excellent. So what we're specifying there is, in fact, what's getting returned. Does it have to be a string? Can we just send an object? Sure, we can try that. So this isn't strict, right? So we can specify it however we want. Okay, so we have a boolean, a string, and we have some sub-object here with an integer. Does that work? Yeah, it just stringifies it for us. We could do whatever we want, and then call json.stringify. We pass it that object or whatever variable, and it'll convert it to a string. So it'll serialize it for us and convert it to a string, which is really nice. But if you have loops, if you have something that's self-referencing, then it's not as nice. But if it's a really simple object, then it works just fine. Okay, so I think Angular is done setting up. Okay, so let's see. So let's go over here, look up Angular getting started, and there's this basic Angular app. And so you can go through component by component and look at it. And it looks like I'm already pushing the limits of the class, but I don't want to hand wave this to the degree that I did with React. But Angular is a very solid framework. So I'll discuss it really quickly. Let's see. So everything is going to be in source. We have that package.json. So if we have to add any additional dependencies, like we did for Express, but Express is server-side, and Angular is for client-side code. So by client-side, I mean stuff that shows up in the browser. And when I say server-side, I mean stuff that the browser requests. So you need something to respond to your requests. So if you're checking out whatever's on ESPN, then the ESPN servers are telling you the scores for all of the games and stuff. Whereas the ESPN client is the one that's handling those responses and demonstrating it in some prettified format. For Google, that really simple search box, the display of the Google art and so forth, that's all on the client side. Whereas all of the magic happens on the server side, where it's actually responding to your search request. So if you have any more client-side dependencies, they'll show up here. You would go into, we have to cd into our project now that we've created it. So cd into generic UI, and then you can npm install whatever you need. So if you want something to make requests for you or help you with those XML HTTP requests, XML XHR requests, then you could use Axios, and that'll help you, or give you kind of a standard form for all of those requests. So you can kind of get a feel for how package.json files help to define the structure of the application. But all of the code that you'll be modifying is here in source. The main file is going to be here, and so it defines an application module, and it bootstraps it and so forth. the index.html file is actually what gets returned. And so this is a template, and then whenever, so it's defined here, build, and so build will, yeah, let me just show you. So you call npm build, fine, npm run scripts build. Let's see. You can choose yes or no. We'll just go with the default, which is no. And so it's building it, and you'll see that it'll create either a public or a build directory here under our project. Eventually. Anyway, so but the thing that it starts off with is this index.html. So this is a template for the file that will be sent to the front end, and you can see it follows some of those basic patterns. And the way Angular works is it defines these atypical HTML tags like approot here, and those correspond to actual modules. So we have main here, which is fine, and then this app component, which has built-in styling. That's fine. Okay, so this is all default stuff for it, and you can see another one of those custom tags here. Okay, and so the selector is defining this HTML tag. So whenever you see, is it over here, approot? Yeah. So whenever you see this tag, then the JavaScript will manage it in such a way that it knows that that needs to be replaced with whatever is associated to the given component. So this is saying, hey, I'm actually approot. So anywhere you see approot, call on me. I know what's going on. And so it sets this custom property called title, and that's generic UI. And then the HTML that's associated to this component, the template, is defined here, right? So replace this tag with the thing that's in here, and supply these styles, and then any logic or values that are in here should be made available to things using the special syntax in this file, right? So if you're looking for something that looks like HTML, then you go here to app component. So this gets replaced, right? So find this, replace it with this. So it gets replaced with this. And then we saw that title reference earlier. No. Right. And so this is that binding operator. So this curly brace, and then variable name says, okay, well, I'm going to use a variable from my component, or a property defined in my component, and so take this value. And so it can be an integer, it can be a string, or whatever, but it's going to bind it to that location, and so it'll make that substitution. So this will get replaced with everything, right? So it'll match here and replace it with this, and so, which is all of this whole file, and then it'll again go through and it'll parse out anything that is of this format, and it'll take it from the component and plug it in. So generic UI would pop up here, and then anywhere else that's following this this pattern. And so I promised that I would discuss design patterns a little more, and so this is a decorator. It is something that extends the class, and we provide it with these specifications. So we give it a selector and we give it a template. And we give it that. Unfortunately, you'll have to dig into Angular a little more on your own if you want. But okay, so last thing, distribution. These are the distribution files that were generated whenever we built our project. And so this index.html, which is our starting point, is essentially copied over here, and it's extremely similar, but you'll see that we've changed, or that we've added all of these scripts, right? So all of these scripts get referenced here, and then whenever they're finished downloading, then the app will begin to render, and so it handles a lot of the logic, like wait to attempt to do all of my JavaScript magic until every script on the body has loaded. And then it also defines these additional HTML tags for us, and make sure that that doesn't generate errors, and it handles all of the fallback logic. And so these frameworks are extremely useful whenever you're doing new development, so that whether you're new or experienced, just to have it all templated for you is just such a dream. It's a great way to get started whenever you're doing this. Anyway, so you would take these files and you would copy them on your server, and if you went, we would have to do a little bit of extra root work to make sure that if they went to root, that it responded with our index.html file instead of this. So we'll not be doing that because I'm several minutes over. But yeah, that's a starting point. So it's really simple to create a project. It's really simple to create a server. There's these tutorials, and you just go down and you follow them. And Angular does a great job of documentation. I learned React at some point, so I'm sure that there's tutorials around for that. Yeah, so this shows how you can create lists and so forth, using the certain syntax. And so just go through the motions of doing one of these tutorials, and you'll see that it's not beyond your reach. This is productive labor, in that you can gain a new skill just by a productive burn of your time. Okay, so that's it. Sorry, I'm way over. Have a great weekend, and I'll speak to y'all on Tuesday.